Hello students, in this video we will be studying about the deflection of a falling mass. We have been studying the fictitious forces, the centrifugal force and the Coriolis force. Due to Coriolis force, when a freely falling mass on earth gets deflected horizontally. So we are going into it. Because of Coriolis force, falling objects on earth are deflected horizontally. For instance, consider a mass m at a distance r from the center of earth. This is earth. It is rotating at an angular velocity omega, and in the polar coordinate system, this is the direction of r, radial direction, theta, the tangential direction. So a mass dropped from a tower lands to the east of a plumbed line from the release point. So when this mass gets released to the ground, it gets shifted towards east. In this example, we will be calculating the deflection of the mass m dropped from a tower of height h at the equator. Okay. Here our coordinate system is a rotating coordinate system, and we have the components r and theta fixed to earth. Now we know that in the rotational coordinate system, the apparent force on m is given by F is equal to minus mg r, which is a real force, plus two terms. These are the fictitious forces, which are the centrifugal force as well as Coriolis force. Okay. So now we are going to find out what is the apparent force. We know that the gravitational force as well as the centrifugal force are radial. They have a radial direction. It acts along the radius from the center of earth, right? And if we drop a mass m from rest, the Coriolis force is in the equatorial plane. Equatorial plane, or it is the plane defined by the great circle of the equator. So the mass will be falling in that plane. So the mass is confined to the equatorial plane. So we have, using r and theta, we have the relation for the velocity. Rotational velocity is equal to r dot unit vector r plus r theta dot unit vector theta. So now we have to find out the equation of apparent force. In this we have to calculate first of all omega cross v rotational as well as omega cross r. So omega cross v rotational, we substitute v rotational here. You get the relation. During cross product, you get the unit vectors. Omega cross r dot unit vector r will be omega r dot theta. And the second term you get minus r omega theta dot unit vector r. So this term contains two terms, one along the radial direction, the second along the tangential direction. Similarly, the second term omega cross r is equal to omega square r in the radial direction. So this equation is splitted into two equations, one the radial part and other is the tangential part. So our radial part contains the term, this term and this term. So our equation Fr, a radial component of the force, is equal to minus mg plus 2m omega theta dot r plus m omega square r. And the tangential component of theta is equal to minus 2m r dot omega, this term. Okay, so we got these two equations. Now we have the radial equation of motion. Left side is f of r. So we have to find out f of r, which is equal to ma. F is equal to ma, where a is the acceleration in the rotational frame. So using that relation, from this relation we find out the acceleration for rotational. First you derive this equation for a single time. So we get acceleration in the rotational frame. From that we split the two terms along the radial as well as the tangential direction. Therefore, the left side you get this term m r double dot minus m r theta dot square is equal to minus mg plus 2m omega theta dot r plus m omega square r. Okay. Since m is falling vertically, we know that omega is the rotational velocity of Earth. This value is much greater than theta dot. Okay, since the mass is falling vertically, theta is a very small value and theta dot is approximately 0, right? So we can neglect the terms containing theta dot. So we neglect this term as well as this term. Okay, so you get the equation, you cancel m throughout, you get the relation as r double dot is approximately equal to minus g plus omega square r. Okay, this is our radial equation of motion. So the radial equation of motion is given by equation number 1. Now the tangential equation is the second part, m r theta double dot plus 2m r dot theta dot, that is equal to minus 2m r dot omega. Okay, this is the tangential equation. Here too we take this approximation, omega dot is much less than theta dot is much less than omega. So you get this equation as r theta double dot is approximately equal to minus 2r dot omega. Okay, now in this equation we know r is nothing but radius of Earth plus a height h. So comparing to re, h is very small. So we approximate r is equal to re, radius of Earth. So in the equation 1, which is the radial equation, the equation for r double dot is equal to minus g plus omega square re, or that is equal to minus g dash, where g dash is equal to g, the actual value of acceleration due to gravity, minus omega square re, which is the centrifugal term. So g dash is the apparent acceleration due to gravity as observed on Earth. So g has been changing during the rotation of Earth. So there is a change in the value of g during rotation by this much amount. There is a decrease in g, right? So we drop the prime factor for simplicity. So later in the later sections we will be taking g alone, not g dash. Now we take the radial equation, r double dot is equal to minus g, or r dot. On integrating you get r dot is equal to minus gt. Again on integration you get r is equal to r0 minus half gt square. Okay, now in the radial equation if we substitute this value r dot as minus gt, you get the equation 2 which is the tangential equation, r theta double dot is equal to 2 gt omega. Okay, so here you get the tangential equation of motion, or theta double dot is equal to 2g omega by re into t. We use the same approximation, r is approximately taken as small re, right? On integrating you get theta dot, and on again integrating you get theta is equal to 1 by 3 g omega by re t cube. Okay, so this is the amount of deflection you feel. This is the amount of angular deflection along towards the east direction for the freely falling mass. The amount is 1 by 3 g omega re into t cube. T is the time at which we are calculating omega. Now let t is the time for to fall the distance h. We know that r minus r0 is equal to minus h, or that is equal to minus half gt square. This is got from the Newton's equations of motion. S is equal to ut plus half at square. You get this relation. From this equation, we know that time of fall t is equal to, equating these two equations, you get root 2h by g. On substituting t cube here, you get y is equal to, what is y in this equation? Y is equal to re into theta. Arc by radius is equal to angle. So theta into re is equal to y. Therefore, y is equal to 1 by 3 g omega 2h by g whole raised to 3 by 2. So this is the horizontal distance moved by the falling mass towards the east direction. Now we calculate the amount of, or the distance of y for earth. We know that omega is equal to 2 pi radians per day. That means earth is rotating once in a day, or it is covering a angle of 2 pi radians. It is approximately equal to 7.3 into 10 raised to minus 5 radians per second. And you know g is equal to 9.8 meter per second square. For a tower of 50 meter height, h is equal to 50. Substituting all in this equation, you get y is equal to 0.77 centimeter. So a distance of 0.77 has been displaced during the free fall by a mass m from the height 50 meter. Since theta is a positive value, the deflection is towards east. So by the rotation of earth, a freely falling mass is deflected towards some direction, towards east direction horizontally, due to the rotational motion of earth. Okay.